our video got cut, so here's the continuation. So for h of f of x, this simplifies into another x. This is actually telling us something about the relationship of f and h. We'll get there. We'll discuss what that is in the near future. In your end, I guess you can read about it now or keep that in mind. Now, since we're operating on functions to come up with new ones, of course, the domain should be taken consideration. Since we come up with a new function, or we may come up with a new function sometimes, we can get the same exact function. That would depend on the operations, of course. Now, the domains will have to be adjusted. The domain of f, for example, is different from the domain of another function, g. They have to, um, what do you call this, compensate for the result of whatever operations between f and g is. So, again, as you'll see in the slide, just remember that for the domains of f and g, if there's a sum, a difference, or a product, the domain of the result will be the domains, the intersection of the domains of the functions f and g originally. But for quotients, because we have that restriction where the denominator cannot be zero, we have to make sure that we do not include values for x that makes the resulting quotient of f with g have a denominator of zero. So to illustrate this further, let's look into examples. Here are the operations. So f of x equals 3x over x minus 3, g of x is 3x squared plus 4, and h of x is negative 2 times the square root of x squared minus 4. So the domain uh, of each function separately are as follows. F of x is a quotient 3x over x minus 3, so we have to make sure that the denominator cannot be 3, so exclude 3 from the domain. G of x is 3x squared plus 4. It's a polynomial function, so no restrictions for its domain. Then we have h of x, where it involves a root. So we cannot get imaginary numbers. So we have to make sure that those are those restrictions are followed. Now, if we take f minus g of x, that means we end up with this function, the result of which, as you see, still involves the denominator x minus 3. So again, we cannot have 3 in the domain of f minus g. While for h divided by g of x, again it's g in this case, in the denominator, 3x squared plus 4, does it become 0 at some point or at some value of x? 3x squared plus 4 can never be 0. But h of x cannot have um, a negative number inside the radical, the square root. So we have to take that into consideration. We end up with this domain. And then for g of h of x, again, this one is a composition. Compositions are tricky because the domain of, in this case, h of x will give us outputs. And those outputs are going to be used into g. But we just have to make sure that whenever we consider the domain, when it's composition, the restriction should carry over the composition. So if we do the composition, we get this function here, 3 times negative 2 squared of x squared minus 4. That leaves us with 12x squared minus 44, simplified. So what happens for its domain? It's going to be this. Although 12x squared minus 44 is a polynomial function, initially it looks that the domain will be composed of all real numbers, no restrictions. But again, since we used a function with a restriction, h of x, the restriction for h of x should also take effect in the result of the composition. Last one for this slide is f of h of x, where we end up with this. H of x goes into f, so we end up with this function right here. So we have a denominator and we have a radical to deal with, so those restrictions should be considered. We get this domain. The next video, I'll show you how we get those specific domains. We'll tackle the graphical analysis of it. So, see you on the next video.